Hi, my name is Taylor Schorler, and today I'll be presenting our paper titled Signing in 4 Public Software Package Registries, Quantity, Quality, and Influencing Factors. This work was part of my master's thesis, so big thanks to Dr. James C. Davis, my advisor, as well as the other co-authors from Purdue on this paper. This work was made possible by support from Cisco, Google, and the National Science Foundation. Additionally, I'd like to thank the Purdue Military Research Institute for their help along the way. We make the following contributions in this paper. First, we provide up-to-date measurements of software signing practices in 4 major package registries. This includes both the quantity, so how many signatures there are, and the quality, so how good are each of those signatures. Prior works have conducted limited scale measurements and have typically not measured more than one registry. So we attempt to bridge that gap by providing multiple measurements over several registries. And then secondly, we perform quasi-experiments to estimate the effect of factors on signing practices. What we find in this regard is that policies have a notable effect on quantity, tooling has a notable effect on quality, getting started is the hard part, and then finally, cybersecurity events such as cyber attacks or different standards released have little impact on the adoption of signatures. Now for a little bit of background on our paper. Provenance is a key topic within software supply chain security. Provenance is essentially the origin or where an artifact in the software supply chain came from. So in a typical example, you might have upstream software. So as an example, PySQLite 3 is a package on PyPy that allows the user to interface with an SQLite 3 database. And then you and your software may import that and then later use it in your code to connect to some database. Now, downstream, somebody may want to use your software. So you might publish that to GitHub or back to PyPy or some other package registry. And the question really becomes, where's the provenance? Where are these things coming from? And how can we guarantee what the origin of some of these artifacts in the software supply chain are? Now, a fundamental way to get some of that provenance within a software supply chain is a technique called signing. Signing provides a cryptographic proof of the origin of an artifact within a software supply chain. This is a cryptographic method whereby a original sender, so Alice in this example, this is taken from Wikipedia, will have a message, create a signature for it using their private key, send that message and signature to Bob, the receiver, and then Bob will use Alice's public key to verify that message. And this provides 2 guarantees within the system. First, it shows that the signed artifact, so the message in this case, was created by a particular identity, so Alice, and then it also shows that the artifact has not changed since it has been signed. This does not necessarily guarantee good software, or in this case, a good message. You can imagine that Alice may have said something mean. In the same way, you can sign a software artifact, but that doesn't necessarily mean it's a good artifact. But what it does tell you is that it was created by the person you think it was created by, and then it hasn't changed along the way. Now, the actual process of signing varies between different signing tools, but in our paper, we outline a general framework for how signing takes place. I won't go into this in too much detail, but essentially what happens is, as I said before, somebody creates a piece of software and also creates a signature with it. That signature is generated from a public-private key pair, and then the signature, key, and software are published to registries. Now, an end user then takes the collection of the package, the signature, and the public key, and then checks the signature with that package and ends up with a verified package. There are, however, many ways that this process can go wrong. The numbers on this diagram indicate points of failure, and we go into a little bit more depth in the paper, but for brevity, I'll identify two trends. So the orange numbers indicate some method where either the signer or the user fails to either upload, publish, or discover the signature. So there's not necessarily something wrong with cryptographically, but somebody has failed to either upload or create or find. The other way, marked in red, is that there can be some sort of cryptographic error. And so typically this is something where maybe the key is expired or the key's been revoked, or maybe there's some sort of mismatch cryptographically between the key and the signature. In the previous couple of slides, I talked about how signing happens and maybe some of the ways that it can go wrong. So we devised a signing adoption theory to try to explain the maintainer's decision to sign and to sign well. This figure depicts that theory. Influenced by behavioral economics, we devised a simple theory that essentially states that incentives influence the maintainer's decision whether or not to sign. So first of all, they decide whether or not to create a signature. If not, there's no signature. And then if they do, the question is, do they create one correctly? If they don't, there's a signing failure of some sort. And if they do, then you end up with a good signature that provides cryptographic guarantees of the provenance of a software artifact. In our paper, we consider 4 different incentives, although these aren't totally inclusive, others may exist. The first of which is registry policies, and these are essentially policies that either explicitly encourage or discourage software signing within an ecosystem. Next is dedicated tooling, and these are tools which simplify the signing workflow in some sort of way. The next is some sort of signing event. So these are cybersecurity events such as attacks or the publication of new standards, whether by the industry or in government. And then finally, we discuss high startup costs, which is essentially the first signature might be harder to create than others. For this talk, I'll only focus on registry policies and signing events. For more details, check out our paper. In our paper, we divide our research questions into 2 themes. They are as follows. So theme 1 is measuring signing in 4 package registries. So for RQ1, we seek to measure the quantity and quality of signing in those registries. This relates to the number of signatures present and the quality of those signatures, so whether or not there are failure modes present. And then for RQ2, we seek to see how that changes over time. The second theme investigates signing incentives. So RQ3 is how do signing incentives influence signature adoption? I mentioned there are 4 different incentives that we investigate in our paper. For each of these, we discuss or create a hypothesis, but I will only talk about 2 today. So hypothesis 1 is that registry policies that explicitly encourage or discourage software signing will have the corresponding direct effect on signing quantity. And then hypothesis 2 is that cybersecurity events such as cyber attacks or the publication of government or industry standards will increase signing adoption, and that's quantity and quality. And so you can see this in the table below, what the factor is and what our expectation for that factor is. Next, I'll talk a little bit about how we aim to answer our research questions. First, we select a series of registries. So in our case, we selected PyPy, Maven Central, Docker Hub, and Hugging Face. These registries correspond to several different modes of software types. So we have traditional software, container images, and machine learning. The next thing we do is we collect a series of packages from each of these registries and then filter those packages down to those packages that we're interested in, namely those within a given time range and that have at least 5 versions. Next, we measure signatures across all of the remaining packages, and then we evaluate the adoption along time axes and then along our influencing factors. Here are our results. For RQ1, current quantity and quality of signatures, this table summarizes our findings. This row shows the percent of artifacts which have a signature on each of our registries that we analyzed. Note that, aside from Maven Central, most of these registries have a very low signing rate. In 2023, for example, all of the registries had less than 1% of their artifacts signed. Among signed artifacts, there's a sizable number of them that have something wrong with them. So you can see that the number of good signatures among these platforms is not 100, except for Docker Hub. Now, you might be wondering why Docker Hub is different and why Maven is different. So Maven Central provides or forces users to sign their packages, so they mandate signing, and Docker has its own tool for signing called Docker Content Trust. We find and believe in our paper that these are contributing factors to these differences in signing. For RQ2, we wanted to see the change in signing over time. Here's one way that we measured that. There's a little bit more content in our paper, but this chart shows the quantity, expresses a percentage of signing over time for each of the registries. So at the top in the blue, you notice that Maven Central remains relatively high over time. Next, you have this orange line, which is Docker. There's a little bit of a bump that goes from here to here, and this is an increased period of signing. And then you have Hugging Face. So these large spikes between 2017 and early 2020 are actually due to the low amount of packages on the platform. So this is a very low sampling rate between here and here, but after this point, it drops to nearly nothing. And then PyPy is this red line, and so you can see PyPy has some number of signatures, but declines until signing was eventually removed from the platform in late 2023. For RQ3, we hope to see what the influence of incentives were on signature adoption. So if you recall, we were going to discuss two of the hypotheses within this presentation. There are two more in the paper. And the first one is the effect of registry policies, and the second is the effect of cybersecurity events. Now, to test these, we actually came up with a list of policies and different events to try to see if there was some sort of impact on each of these events and policies. And so in summary, what we found is that for registry policies, they seem to affect quantity of signatures, but not quality. And then in terms of the signing events that we studied, we weren't actually able to find any instances where there was a statistically significant change in signing. For hypothesis 1, registry policies, I'll show you a little bit of the justification for our results. More details exist in the paper. So first of all, at this point, the PyPy actually begins to de-emphasize their PGP signing. And so you notice that after this point, that signing starts to trickle down. On Docker Hub, at this point, they provide an update to their platform that actually increases a little bit of provenance. And so this occurs right before actually the bump that happens within Docker that we occurred earlier. And then the last thing to note is that this large difference between all of the registries we studied and Maven Central highlights the importance of their decision to start mandating signatures. So now I'll talk a little bit about the justifications for our results for the second hypothesis. Again, more details in the paper. At this point was the Docker Hub hack in April of 2019. But we can see that that spike in Docker Hub didn't occur until much later, actually, about 9 months. SolarWinds, which was a massive software supply chain attack, occurred at this point. And as you can see, although Maven's trending upwards, none of the other registries statistically change much. We also observed many other attacks, and you could plot them on this graph, but it would become busy, but none of them seemed to have any sort of impact along with any of the other standards published. So here are some of our key takeaways from the paper. So first of all, signing practices vary widely. And if we want to use this technology to help secure our software supply chains, it's not in a great state currently. Any empirical research has its limitations, and ours is that our results aren't causative. However, there's a very strong correlation that registry operators can influence signing with their policies. This is a great way for a great non-technical or limited technical way that registry operators can increase signing in their registries. Another reason for this is that events don't really seem to affect maintainers. This is kind of counterintuitive. We'd expect that big attacks or standards published would maybe have some sort of effect on communities, but it seems like maintainers don't really seem to take action unless they're required to. The last thing is that emerging tools do look promising. Sigstore, for example, seeks to remove a lot of the overhead burden of managing keys, for example, and this may help decrease failure modes within signing. Thank you for listening to my talk. If you have any questions, feel free to reach out or take a look at our paper. Thank you again, and take care.